Okay, so um, today won't be fun because it's just gonna be review, right? I mean, it's gonna be linear algebra today. So um, you all probably know most of this, so it might be a bit boring. So okay, but I'll sort of tell you the motivation. Yeah. So but it's gonna be general. Yeah. So we're not gonna in math. What is it? Math two, no, it's 3A, right? In math 3A, you really only learned it over like R or like C. So here it's for F general, right? So F a field. So let me just say math 3A. Is it 3A? Can someone confirm? That's the linear algebra, right? So this is F is like R or Q or C. But now you know F could be like ZP, right? So so for the purposes of this, I'm gonna write V space as vector space. Yeah, in vector space over F. So is an abelian group V. Yeah, so you can't really multiply. You can't always multiply two elements in V, but under addition. But you can multiply elements in F with elements in V. So and scalar multiplication such that for all A, B, and F, alpha, beta, and V, right? So A times alpha is in V. So basically when you multiply by your scalar, you stay in your vector space. And if I multiply, A to B, it's the same as multiplying in your field here and then multiplying by alpha. Yeah. So note here, I'm multiplying the scalar with the element in V. Yeah. Here it's multiplication in the field F. Yeah. So, and then we have the obvious distributive property. So if I add two elements in F, so this is in F, right? Times alpha, that's the same as A alpha plus B alpha. And now, but V is an abelian group under addition. So what about if I add two elements in V? So this is in V. Then this is A alpha plus A beta. And obviously 1 times alpha is alpha. Yeah. So examples you include like Rn is a vector space over R, right? You can multiply vectors by scalars, right? So the scalars are like elements in R. Your polynomial ring is vector space over F, right? You can multiply polynomials by constants. You have like the set of n by n matrices over F. This is vector space over F. Yeah, so you could certainly multiply matrices by constants, right? So we're gonna note that the most important is extension fields. Yeah, E over F. So the example to have in mind is even a very simple one, like Q adjoin root 2. Yeah. So this is a vector space over Q, but we'll check that later. Yeah. Uh, Okay. Everyone clear on this? Okay. So moving on, I'm just gonna state this theorem because they're proving everything from scratch, right? If V is vector space over F, then 0 times alpha equals 0, and A times 0 equals 0. So when you multiply 0 by any element to any element in V, it's 0, and to any element in yes, it is. I mean, the operation, it's under addition, right? I mean, if you add two matrices, A plus B is B plus A, right? So, okay. Now we're gonna define a basis. So we're gonna let V equal vector space over F. So if V equals vector space over F, and then we say the vectors in subset S equals, so S could be infinite, yeah? So S could be, alpha I for I and I. Yeah, it could be some really crazy infinite set of V span or generates, if you like, V if for every beta in V, I could express beta as a sort of like a finite linear combination of, you know, elements in that set. Yeah, for AI and F and alpha ij in S. Yeah, so S could be infinite. Yeah, you have an infinite spanning set, but like every element is a finite linear combination of, of these elements in S. So yeah, again, we say some AI alpha aj alpha ij. Call from so okay, so we say is a linear combination. Okay, of alpha ij. Yeah, so an example would be something like, you know, the set like 0, 0, 1. I don't know why I wrote that first. 0, 1, 0, and 1, 0, 0. So these span R3. Yeah. So in my case, V equals R3, F is R. Yeah. Because given any element in R3, like given ABC, right? Like I could write this as A times 0, 0, no, sorry, C times 0, 0, 1 plus B times 0, 1, 0 and A times 1, 0, 0. Yeah. So you see that this set S spans R3. Yeah. And most certainly R3 spans R3. Yeah. If I just take all elements R3, it spans. Yeah. So of course, if S already spans R3, if I add any more elements, it's still gonna span R3, right? So definition. So S need not be finite, but a vector space over F is finite dimensional if there is a finite subset of V which spans V. Yeah, so if the set that spans V is finite, then you're finite dimensional. Everyone good so far? Yes, no. Okay, so in accordance to what I just said earlier, right? If you add anything to the set, it still spans, right? Like this thing, if this thing spans R3 already, right? Spans R3. Then this certainly spans R3, right? If I just include like 1, 1, 1. Yeah? Does everyone agree with this? So, but like 1, 1, 1, we sort of say this is like redundant, right? Redundant. So we want a way of saying, so think of span as you have enough, right? There's enough, in this case, there's enough vectors, right? And but we want something that says we not too much, right? Just we need like just enough. So the word for that is linear independent. So for the not too much. So so let me see. So the vectors in S, right, equals, let me just call this alpha I for I and I are linearly independent over F if for all alpha I and S, alpha J, AJ, sorry, AJ and F, and in Z, if the sum, like J equals 1 to N, AJ alpha IJ is 0. So if I take any linear combination of these of elements in S, any finite linear combination is 0. This is if and only if AJ equals 0 for all J. Yeah. So you see here, right? I can get 0 without all coefficients being 0 in this set because suppose, A100 plus B 010 plus C001 equals 0. If these were linearly independent, then A, B, C, D is 0. Yeah, so that's the only solution. But obviously it's not, right? Because example, like I could take A to be 1, B to be 1, C to be 1, and D to be 1, or -1, sorry. Yeah. So this is like a non-trivial solution, right? So you see that these are not linearly independent. As opposed to here, right? If the set S above, this is linearly independent, right? Because if I tell you this is 0, well, this thing is just ABC. Yeah, and for ABC to equal 0, 0, 0, well, obviously A has to be 0, B has to be 0, C has to be 0. Does everyone follow? So again, span is you have enough. Linear independent is you don't include redundant stuff. Okay. Yeah. Okay, so now we get define definition V vector space over F vectors in subset B equals, again, I don't know why they changed from like S to B, but BI for I and I. A V form a basis of V if and only if, they span V and are linearly independent. So what I said above, I mean, not above, in the previous page, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, they form a basis of R3, right? So, yeah, and then we say number of elements in basis is dimension of V over F. Yeah. And I mean, if the elements is infinite, then we just say it's not finite dimensional, it's infinite dimension. Yeah. So with that being said, let's do an example. Yeah. Let's do Q adjoin root 2. Let's show this is actually a vector space over Q. Yeah. So this thing, how do elements in here look like? Can anyone tell me? It's the set of what? Like A plus B root 2. Yeah. Everyone agree? Or remember? Not agree. Okay. Well, okay, let's show this is this is certainly a vector space, right? Because over Q, because it's a abelian group, obviously, and I could honestly multiply by anything in Q. So the fact that that's a vector space is not that hard. So I claim the basis over Q is given by it's 1 and root 2. Yeah. So let's check it's a basis, right? Does it span Q adjoin root 2? Well, can I write any element in Q adjoin root 2 as a linear combination of these two elements? Well, yes. So given A plus B root 2, right? I could write it as a linear combination of these two elements, right? It's A times 1 plus B times root 2, right? Not that hard, right? So this set spans Q of root 2. Everyone follow? No, not that hard. Now let's check linear independent, right? Suppose there exists linear combination, right? There exists A times 1 plus B times root 2 equals 0. I need to show that this implies A and B is 0. Well, that's kind of obvious, right? Because you're just matching coefficients, right? So this is just on one hand, this is A plus B root 2, and this is 0 plus 0 root 2. So matching these coefficients, B must be 0. Matching these, A must be 0. So it's linearly independent, right? Does everyone follow? So we have Q of root 2 is vector space over Q of dimension 2. Does everyone follow? Okay. Well, let me just give you an idea of why we do this. Yeah. Like if you were going to show these two fields were not isomorphic, right? This is idea because we didn't really go over this yet. So this thing is you could show it's three-dimensional over Q. And I mean for these to be isomorphic as fields, they need to be isomorphic as vector spaces over Q. And they're not because this is three-dimensional and this is two-dimensional. The fact it's two-dimensional, I just showed it right here, right? So the problem, you could show this thing is the elements here is one is A plus B cube root of 5 plus C cube root of 5 cubed squared. So like here, right? It's, how do I say this? Yeah, it's like, this is three-dimensional. And I mean, you can see the dimension is, in fact, I don't think you even need that. You could just say this is the dimension is the degree of the irreducible polynomial over Q. Yeah, and this is the degree of irreducible polynomial over of root 2. So I think by the time you learn this, you don't even need to write out the elements. You could just say this is like, degree 2 over Q and the other one's degree 3. And then you could say they can't really be isomorphic. So that's the idea. Yeah. So these are to show like, sometimes you want to show two algebraic extensions are not isomorphic. So anyhow, that's for later. we didn't really go over isomorphisms of like field extensions. So let's move on. So last thing, fact. Every finite dimensional vector space. So suppose you just check there's a finite basis that spans, right? But you don't know it's linearly independent. Well, this thing says there is some subset of that that's linearly independent. So has and spans, has a basis. Yeah. So a basis always exists for finite dimensional spaces, and any two bases sorry, it's plural. So apparently the plural is with an E basis of finite dimensional vector space has same number of elements. Yeah, so an example would be, I didn't have to choose this, yeah, for this, like this is one choice of a basis. One choice. Yeah, I could choose another one, but I know it has the same number of elements. So I could have chosen like 1 and 1 plus root 2, if you like. Yeah, kind of like here, right? 1, 0, 0. Like there's no reason to choose these, right? Like I could have chosen, for example, another set like this. 1, 1, 1. Yeah. Because the point is I can get 0, 0, 1 by doing this, subtract this, subtract this. Yeah. So the basis is not unique. Yeah. You can always, so you can see like if I take this element here, that's the basis, subtract, the new element I get is still a basis, right? So like here, so the basis doesn't change if you do like addition, subtraction, and scalar multiplication. So that's sort of why in 3A you learn Gaussian elimination. If you recall row reduction. Yeah. It's because doing linear combinations does not really change your, I mean, it doesn't affect the fact that you're a basis. So is everyone clear on this? So let's move on. So I mean, let me just remind you that this is not 120 right now. This is 3A. So if I gave you three vectors, right? How would you check they form a basis of R3? Yeah, yeah, but you learned the easier way in math 3A. Yeah. Yeah, this thing, right? Like I said, doing linear combinations does not change the fact you're a basis, right? So whatever three rows I get after I do Gaussian elimination, those, if those form a basis, the original is a basis. So I mean, let's subtract the first with the second, right? So 1, 1, 0, 0, 1, 1. Did I do this correctly? So yes, yes, yes. No, 0, 1, -1. Yeah, and 0, 1, 1. So what to do next? Well, let's subtract off the so I have 1, 0, 0 on one of them already. So from here, I could subtract the second from the third, I guess. I'm not good with this. I hate algebra. Okay, so 0, 0, -1, -2, right? And then from here, I can get rid of the -1 by multiplying by 2 and then subtracting it from the third row. So you get 0, 1, 0, -2. Hopefully you all know how to do this, right? So 0, 0, -1, and then subtract second from first from second to get 1, 0, 0, 0, 1, 0. And the reason what is the reason you want to, sorry, I divide by -2. So what's the reason you want to row reduce to row echelon form? It's because you know these three span R3, right? Uh, I wrote vectors like this, so it's because you know these three elements span R3, right? That's easy. Does everyone agree? And since doing linear combination doesn't change the fact you're a basis, since these three span R3, these three must span R3. Is everyone clear on that? This is like math 3A. I mean, since these three are a basis for R3, these three are a basis for R3. Yeah. Okay. Let's do some questions and call it a day. So let B, I don't know why they use let S equal alpha I and I. So the one of the questions is show S, so V vector space over F. So S is a subset of V. Show S spans V and is linearly independent, so it forms a basis if you like. If and only if, hold on, I forgot. Let me see the question again. So show that is true. Oh, V finite dimensional, sorry. So V finite dimensional. So if and only if every beta in V can be uniquely, so they're uniquely expressed as a linear combination of alpha I. Yeah. So this is let's go one way, right? So suppose, every beta in V can be uniquely expressed as a linear combination of alpha I. Yeah. So forget the uniquely, right? So just using this fact right here, which part have we shown? Have we shown linearly independent or span? Just from the fact beta can be expressed as a linear combination of the alpha I. Span. Yeah. So from here, right? And since it's finite dimensional, right? Yeah. Okay. So it spans, right? So from here, like S, so just from green underline, green, S spans V. Yeah. Now, suppose that, every is unique, right? So let's suppose that let's suppose there exists, how do I say this? Let's suppose. I'm just going to use A0, A0, alpha I0. Suppose there exists, A0 to AN, yeah, such that this is 0. How do I show that A0 to AN must be 0? Using my assumption. So there's one thing I haven't used yet, right? What is that? There's like one thing in the green underline. So So if we assume not all, not all AI are zero, then I can express then I could express zero in two different ways, right? I could express it like this, or I could express it like this. Yeah, these are two different ways if we assume not all AI are zero. Agree? And that contradicts uniqueness. Yeah, we should only be able to express zero one way. And hopefully the opposite is the same, right? So if I span, then I could I could write everything as a linear combination of the AI. And if I am linearly independent, well, suppose that okay, let me just go this way. So suppose S spans V spans V and R and elements in S are linearly independent. So do you agree that we get just from span, S spans V, we get every beta in V can be expressed as a linear combination of alpha I. Does everyone agree with this? Just from the fact that S spans V? Yes or no? Okay. So from here, right? How do I say this? From here, I want to say, okay, well, so suppose it can't be uniquely expressed. Yeah. Suppose, beta cannot be, so so suppose there are two ways to express beta. Yeah. So beta is A0 alpha I0 plus A and alpha I n. Yeah. And without loss of generality, since we're finite dimensional, I know S is finite, yeah? So I might as well just list everything, yeah? So AI to like AK. I mean, some of them could be zero, yeah? But there are two different ways. A alpha I, alpha 0 all the way to AK alpha K. Yeah? So I might as well just list it all out. Yeah. And then beta could be expressed another way. Does everyone see what happens next? If I subtract, then it's the same argument, right? 0 is A0 minus B0, A0 plus AK minus BK, AK, alpha K. Sorry, these are alphas, alpha K. So now, but since these are two different expressions, not all of these are zero, right? Does everyone see that? Since they're two different ways to express beta. But then again, 0 is just 0 times 0 is 0 times alpha 0 all the way to 0 times alpha k, right? So does everyone see the contradiction? Then there's like the alpha k's are, how do I say it? Sorry. Wrong thing. So from here, right? Sorry, I did the other one. Ignore what I said. So from here, it shows that A0 to AK are not linearly independent. Yeah. I forgot we're going the other way. Because I found I found a linear combination of them, particularly these, right? Alpha 0 plus AK minus BK alpha K, where not all of these are 0, right? And once that happens, once this equals 0 and not all of it are 0, you're not linearly independent, right? If we go back to the definition of linear independence, where is it? They're linearly independent if a linear combination is 0, then all coefficients are 0, right? Here we found a linear combination that is 0, but not all coefficients are 0. Yeah. So they can't be linearly independent. Is everyone clear on this? Sorry, messed up a bit 2 minutes ago. Okay. Yeah, it's just definition. So let's just talk about one more thing. Yeah. So, all right, I'll just explain. So if we let V and V prime be vector spaces over F, right? We could define like a function, right? Phi from V to V prime, and we call it a linear transformation, right? So these are matrices, right? Think of them as matrices of V onto V prime. And what do linear transformations satisfy? Alpha plus beta equals phi of alpha plus phi of beta. And so it's sort of like a homomorphism, right? Except for the multiplication part. There isn't really a multiplication part because you can only multiply scalars to elements in V, right? So this is A times phi of alpha. Yeah. So again, we never define a product in V. Yeah. We would need to give V additional structure, like a field, right? Or a ring for it to have two operations, right? A vector space is only, it's an abelian group under plus. And you could just, and there is multiplication, but only with elements in your field, not elements in V. So, but this is actually enough to sort of talk about like what I said before, right? If I gave you like a cyclic group, right? Everything is determined by where one goes, right? Well, same thing here. So if beta I, so if this set I and I form a basis of V over F, right? Everything everything is determined by where beta I goes for all I. And you can sort of see this, right? Because given alpha and V, since this is a basis for V, I could write alpha as, say, A0 beta I0 plus AK beta IK, right? Then phi of alpha is phi of this. K beta IK, right? And then using the first property, I could split this up. to A0 beta I0 plus dot 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 plus phi of AK beta IK. And now using the second property, I could move the A0 out. So you see, everything's determined by where each of the phi of beta ij's go, right? So it's very similar to a homomorphism in a way, right? Except for a homomorphism, if your group is cyclic, it's generated by like, you know, one thing. So that's all you need to know where that one thing goes. So similar to here, think of like, beta i's generate slash span like your space V. So I just need to know where each basis elements goes to know where everything in V goes. Everyone clear on this? So really I think the more interesting thing we'll cover on Thursday. So it won't be review. We'll actually talk about fields being vector spaces over your smaller field. Everyone good? Okay, cool. I will see you all Thursday then.